All right, so as the title said, I've been developing a technology for the last, I'm not getting younger, I think it's 12 years now, 11 years, that makes use of, microorganisms that can take up electricity and convert CO2 to chemicals. So before I get started with my talk, by the way, I will try to speed up a bit because I thought it was 25 minutes, so I will try to shorten it a little bit. So here's the first list of key messages that I would like you to go home with. The first few ones are pretty trivial, but I think it's pretty important to insist on the trivial part. So the first thing is that microbes are able to take up electricity and convert CO2 to a wide range of chemicals, fuels, feed, and food. And that technology is called microbial electrosynthesis. MES can become one of the needed solution to defossilize the chemical industry. And here I use defossilize because we still need carbon, but we do need to find an alternative to fossil resources to make our carbon products. So how about using CO2? MES is complementary to other CO2 valorizing technologies. And I always put that statement here when I give a lecture, but I think here it's a pretty important statement because as we're going to see in the rest of the day, we have several technologies out there that are worth investigating to valorize carbon dioxide. Microbial electrosynthesis requires multidisciplinary expertise to improve and scale up. And the chunk of my presentation will show you a little bit of the effort that we have been doing in my lab on designing novel reactors to improve performance. And we will see that we got now microbial activities that are in par with syngas fermentation, which is going in the right directions for industrial application of microbial electrosynthesis. But first, before I get to MES, I would like to introduce the institute that I helped co-initiate when I started my group at TU Delft in 2018, which is called the E-Refinery Institute. And our vision there is to accelerate the transition towards sustainable production of chemicals. And to fulfill this vision, we believe that electrochemistry will play a key role in converting simple ingredients like you see here. Let's see if that works. Water, air, electricity, in some cases biomass, to make our chemicals and fuels. And after the end of the lifetime, after using it, we could recover CO2, water, and put it back into our electrochemical system as to fit within a circular economy. At E-Refinery, we developed several routes. We have what we call direct routes, and there we do, and E-Refinery has about 50 PIs, so 50 professors with associated PhDs and postdocs, so it's a pretty big institute. And we are doing some work on water electrolysis in what we call direct electrochemical conversion of CO2 or nitrogen, and also direct electrified biotechnology. So that's where I lead the pillar on microbial electrosynthesis and electrofermentation. And we also have a multi-step routes where we do, for example, where we combine electrochemistry and thermochemical processes, but also what we call e-biorefinery, where we can integrate, for example, an electrochemical step like water electrolysis or CO2 electrolysis to another step, for example, catalyzed by enzymes or fermentation technology. So we are also looking at all this. But today I will talk about microbial electrosynthesis. So what is microbial electrosynthesis? Here you see a schematic representation of an electrochemical system. So I'm sure most of you know what it is. So we have an anode reaction here where we have water oxidation to oxygen and protons. And we have a cathode compartment here where we use typically a carbon-based product, ideally fibrous filamentous or 3D electrodes. Like here you have a carbon felt. And on this carbon felt we have microorganisms that form biofilm on those electrodes. And those biofilms are able to take up electrons from that carbon electrode to convert carbon dioxide to, in this presentation, to a mixture of C2, C4, and C6 carboxylic acid. So acetic acid, butyric acid, and caproic acid or hexanoic acid. So it is a promising technology on paper, but what is missing to make it a reality in industry? So for example, it's promising in the sense that we get pretty high Faraday efficiency. The biofilms is self-repairing and robust. So in my lab, we've operated reactors routinely for more than 2-3 years without too much issues. We produce longer chain carbon products, and here it's longer when you compare with chemical catalysts. So I work a lot with electrochemists that use metals or metal oxides in CO2 electrolyzers, and they mostly produce C1 or C2 molecules. In our case, as I said, we can produce up to C6 and maybe even longer organics. And of course, we don't rely on arable land, and we need little amount of water, energy, and nutrients. But what is missing is that we still are at lab scale after 10 years, and we need to make a step forward into scaling up this technology. And here's a schematic representation of an analysis that I've done with a colleague in an opinion paper a couple of years ago, where we see schematically represented the amount of effort put in different aspects of the technology. And here, for example, in research in the last 10 years. So you see a lot of effort has been towards developing cathode materials, into finding out more microorganisms. But if you look at reactor design, it's a very small word there. That means not much research has been done or devoted to reactor design. So we thought, well, that's typically the type of reactors that has been used a lot in the lab. They are good to do fundamental research, but not so good when you think about scaling up the technology. So we need to think a bit again about reactor design. Historically, the last few years, I've worked with this type of reactors. You see a photo here, and you see me pretending to work on this reactor. I should have removed this photo because it's a little bit embarrassing now. But it's all right. So you see it's a flat plate type of system. So you have an anode here, you have the membrane in between, and this whole thing is a cathode chamber, and the black part is the 3D electrode. And so what we've done here is that we simply force the flow through of the medium through the electrode and recirculate it around like this. And this allowed us to increase productivity quite dramatically. And another aspect that we've done as well is that we operate our reactor in continuous mode. A lot of the research has been done in batch, and we think that operating in batch leads to a lot of limitations. Yeah, I should have also removed that slide. So that's my most pretentious slide. I'm sorry about that. So here you have the organics production rate normalized to a surface area of electrode. And here's the current density on the x-axis, both in logarithmic scales of all or most of the MES studies up to 2020, 2021. And here's the work that the performance that we managed to achieve with this type of reactor. However, we see now we are at about 100, 150 amps per square meter, but we did also a techno-economic assessment, and we found out that you need to get up to 500 to 1,000 amps per square meter for economic viability. So we still have a way to go. That is up to debate and a lot of parameters, by the way. So 500, 1,000, it's approximate, let's say. So when I started my group at the end of 2018 in TU Delft, we are like, okay, let's sum up all the phenomena that could be limiting at different physical scales. So from the nanometer scale to the meter scale. Here you have only a few examples. And the idea was, let's identify what could be limiting and let's overcome those limitations. And to do this, we see MES as a puzzle. You have electrochemistry, you have the microbial catalyst that you need to take care of, you have the reactor environment, but how do we find out what is limiting? We didn't want to do too much try and error anymore, so we decided to involve a little bit of mathematical modeling to identify limitations. So that's what we did with Oriol, one of my PhD students. So we decided to use a multi-scale mathematical model to identify limitations, then based on this knowledge, design a new reactors, and then go to the lab and test this reactor design. So that's what we've done, and that's what I'm going to show you briefly in the next few slides. So we started with our multi-scale model by looking at the microorganisms. I should have mentioned that we are using a mixed microbial culture, which makes it very difficult to model. So we decided let's simplify it and make that mixed microbial culture into one hypothetical organism and look at it as a black box. So we did a simple black box kinetic model when we couple electrochemistry with microbiology. I won't show all the details of the model here, but we showed, and you can have details in that paper, we showed that we could describe not only our reactors and our systems, but also other people's reactors from literature. And we could identify some limitations already. So, for example, we saw that continuous operation leads to a much higher cell density. So that means higher microbial or microorganisms density in the system. So that means higher productivity. And we also saw that CO2 could be limiting performance, even though you feed and you have the feeling that you feed a lot, it can actually be limiting. So you need to account for CO2 supply in your system. So then we went from that microbial kinetic model to a 2D model. So I told you before how the reactor looks like. And you have the biofilm in the middle there. We did fluid dynamic, electrochemistry, and we integrated the microbial kinetic model to this. And again, I'm not going to show you the model itself, but I will tell you what are the main message. So if you look at this state-of-the-art reactor, what we could quickly find out is that we had a preferred flow path through the electrode. So that means the biofilms that would be here, if growing at all, would be not as productive as in the middle of the path. We also had, an uneven biofilm distribution. Of course, we had a high distance between the cathode and the anode, which is creating a lot of energy losses. And we had a lot of dead volumes here. Like if you imagine, if you want to scale this up, right, we wanted to have the end in mind. How do we scale up this system? You cannot really scale up with that much empty space on both sides of the electrode. That will take a lot of footprint. And another thing is that it has a low residence time throughout the electrode, which we wanted to improve. So then we set out to design a new reactor, and we were like, okay, what do we want to do? We want to improve energy efficiency, and we want to increase productivity. So CO2 conversion rate and organics productivity. So we started from there, and then the first step is quite obvious. You just remove the dead volume, you pack it closer to each other, and then you have a flat plate like this. But if you imagine a 1 square meter type or 3 square meter type of reactor, well, you don't want to have an inlet here and an outlet here without dead volumes at all. You would really have a favored flow path from the inlet to the outlet and a lot of dead volume, or a lot of area where the biofilm would not grow. So that would not work. So what we did is that we took inspiration from water electrolyzer, fuel cells, and we just designed a flow path here, a serpentine flow path. But unlike what they do in fuel cells or water electrolyzer, what we did here is actually we filled up this flow channel with our 3D electrode. So that looks like that. So that means, hypothetically, you would increase the residence time from the inlet to the outlet. You would remove all the dead volume. You would increase fluid dynamic through. You would increase biofilm density, and ideally you would reach your target. Here we had a 0.5 centimeter thick. That's still being optimized as we speak. And we went on and 3D printed it. It looks like this is the first version. Now we've improved it quite a lot, but I cannot show that yet. And it looks like this when you 3D print it and assemble it. So I'll walk you through it quickly. So on one side, you have the current collector for the cathode. You have your serpentine chamber with your carbon felt in. You have your membrane. Then you have your anodic plate where you have your anolytes flowing through. And then you have your anode electrodes on the other side. So we went on and then assembled 2 of those reactors and operated them in continuous mode. I will show you the results of only one because of time. So here you see the current density normalized to either the surface area or the electrode volume over time. And here the stars are the state of the art, so the highest performance obtained before. So the first thing is, yes, we operated again for more than 200 days. That's a long biotic MES operation. But then you can imagine that you don't want 100 days to start up a reactor. So that's really not good. We are identifying why that was the case, but the main culprit is that when I moved from Wageningen to Delft, I had to freeze my biomass for 3-4 years before I could start those reactors again. So I assume that they were not very happy after 3-4 years. So it took quite a while to start up. Another thing you can notice is this big dip here. And that was pretty dramatic for my PhD students. Not so much for me. I'm starting to be experienced with crashes. But what happened is we had a leak and everything got, all the liquid leaked out of the reactor. It was open to air, the potentiostat crashed. And that happened on a Friday night before a long weekend. So my PhD student, when he came back on a Tuesday, was not so happy. But I was like, let's not panic. Let's refill it again, fix the leak, fill it up again, and then, as expected, as I was hoping at least, it started up again, and it even got better. So that shows highly robust system. We have pretty high current density. I have to admit it got a little bit noisy there, but if you look at the minute scale, it's not that noisy. It's just that it's very compact. Oops, sorry. We actually had high Faradic efficiency even at the high current density, which was quite interesting for us. We were afraid that we would get high current, but not many electrons going to the final product. But it was the case, so it was nice to see. And we decreased the cell voltage required by 1 volt compared to the other reactor designs that I showed you before. So the energy efficiency got also better. So overall, it's a pretty stable and robust system, even though it took a long time to start up. So that's about the current. But if we look at the product trend, you see here the organics concentration over time. So keep in mind, again, it's not a batch. It's a continuously operated system. So you see acetate in blue, butyrate in orange, and caprate in green. Yeah. So we could manage again to produce C4 and C6 with a new design. I put it here because not many people still manage to produce C4 and C6, so it's good to see that those reactors could. Unfortunately, we were still not really reaching a steady state after more than 200 days, so that's also not so good. According to what we know, at least, we could obtain the highest butyrate production or concentration in MES continuously operated to date, up to 18 grams per liter. And what's interesting, and we are still investigating it, is that here you see the carbon selectivity before the crash and after the crash. So before the crash, we had a majority of acetate, but then after the crash, we had much more into butyrate and caprate, which is what we want. I forgot to mention that our target product is a longer chain product, so C6, and then C4, and then the list is C2. So we are trying to understand exactly what happened here. And here you see a comparative performance of the two systems, the previous state-of-the-art and the new system in volumetric productivity. And we see here that we managed to have a pretty decent increase of production rate up to 50 kilograms per cubic meter per day. What's interesting is volumetric current density, let's say kiloamps per cubic meter. We could get up to 35 kiloamps per cubic meter compared to the state-of-the-art of 7.9. So we are getting, I'm sorry, I'm quite sweating, it's hot. So it's quite high current density, but we are not there yet to the target. So it's nice in terms of our performance of reactors, but what we wanted to find out is, in MES so far, or in bioelectrochemical system, we have performance normalized to dimension of reactors. But if you look at a chemical process catalyzed by a chemical catalyst or fermentation technology, performance are always normalized to the amount of catalyst at any given time in your system. But that's not what we do in the microbial electrochemistry. So we wanted to develop a simple yet elegant method to be able to quantify the amount of biofilm at any given moment in your reactor, so that you could determine biomass specific rate of your system. So before, what you would do is that you run a reactor for a year, you open it, then you get your nicely looking biofilm, and then you could quantify it, but then you would have only one data point at the end, and we wanted something over time. So without going too much into details, we just actually did a simple method following ammonium concentration and OD to be able to actually quantify at any given moment how much ammonium is consumed, and we know then how much goes into planktonic cells, and the difference would be how much stays in biofilm. So we did that, and then we could then determine the amount of biofilm at any given moment. So in the old type of reactors, that's what you see. So here's the amount of biomass in biofilm over time, and we would get a density of about 4 millimole per cubic centimeter. And out of this, you would find out that after 50 days or so, almost 100% of this biomass would be in biofilm. So in our system, it's really driven by biofilm and very little or not at all by planktonic cells. And then if you look at the new design, you could actually obtain a 4 times higher density of biofilm. So we would have much more microorganisms per volume unit of our system. And here, I know it's a little bit messy, but you actually see QP. So it's a biomass-specific production rate of organics. So in mole of carbon into product per mole of biomass per day of the 2 reactors that we operated. So it's a bit messy at the end, but you would, let's assume you are at about 10 mole of carbon per mole of biomass per day. And if you compare that with a syngas fermentation and chain elongation starting from ethanol and acetate. So first of all, the state of the art of MES is all the way at the bottom here. So we are about 60 times higher now. And if you look at syngas fermentation, actually, we are in the same range of microbial activity in MES than in syngas fermentation and also chain elongation fermentation. So that was pretty nice to see, and that allows us to actually now be able to determine how microorganisms are doing in MES system. And now, as I said, we are in par with syngas fermentation, so there is a way to go. So we still open our reactors, of course, after operation. So that looks like this. Depending on the audience, I say that looks disgusting, but actually for you, you are probably used to this. And when you open your reactors, you are pretty happy to see this. It's a lot of biofilm, a lot of biomass. And so that's from the membrane side, and that's on the current collector side. So it was developing throughout the whole electrode from the inlet to the outlet, and also throughout the carbon felt. Here you see some scanning electron microscopy images. You see a very compact biofilm. I should mention now, before I get questions, I always get this one: which bacteria you have there? I cannot answer yet. We have to wait a few more months to do this. We are doing full omics characterization, multi-omics characterization of our biofilm and of our system. So I promise it's gonna come up soon. So you just have to be patient a little bit. So just to wrap up, I don't know how I did in time. Did we manage to get to our target productivity? Well, we did increase microbial activity to levels that are very interesting for industrial application. But if we compare with requirement electrochemically, we are still a bit off, maybe of a factor 2 or 3 from the targets to be reached. But there is definitely a way forward, and definitely I think we are on the right track, and we can move forward with the technology. We still have a few limitations to overcome, but yeah, we are getting there. And I'd like to indeed thanks. As I said, I'm not doing the work in the lab anymore, so all those people are doing this work. So I'd like to thank them, even though they are not here, and of course the funding that I've got from the government, but also some companies and my collaborators. And thank you for your attention. It's straight. Okay.
Thank you, Ludo. You can hold your questions for the end of the session while he takes some water and some refreshment.
I don't know if I should.
Yeah. So the next speaker to put some sweat here, it's Falk Harnisch, who is going to present the approach of our project Vivaldi. So very happy to have him on board, and the floor is yours, Falk.
So welcome also from my side, and thank you for the introduction. And certainly we don't have CO2 limitation here, and it's more the oxygen that we are missing. So it's a pleasure for me now to introduce to you first the general concept about on electrobiorefineries and how to make organic acids from CO2 on a very, let's say, global level. And afterwards, I will take you through a small journey from how to interface electrochemistry for CO2 reduction reaction with biological conversion, and also give an outlook what we are in Vivaldi actually targeting as next step. So, and I think the status quo you're all aware with, and this is that when we think about biorefineries, so we have here the electric energy sector, so we can make renewable electric energy, and here we have the biomass sector, meaning we can use renewable feedstock. Food versus feed competition is, of course, something to be concerned of. And then we have different process steps that finally yield to gaseous, liquid, or even solid products. But what is missing to a certain extent is the interconnection of these two fields, so meaning of the electric energy sector as well as the process or biorefinery sector. And here, of course, electrochemistry can play an important role because by nature, it links the conversion of electric energy into chemical energy and vice versa. And you can see here different pathways how to link link electric energy sector with the bioconversion sector. And this, of course, includes making electric energy from biomass, but also a lot of other pathways. And you can also see the potential advantages that it has of doing this interlinking of electric energy usage and storage, maybe even, and the bioconversion. And before talking about specific details today, I want to say thank you to the people that, like me, like for Ludo, I'm not anymore standing in the lab, and I can't find, nothing in the shelves, I have to admit, that actually do the work here. You can see them nicely pictured here, and especially attention, apart from the people that are currently in the lab, like Pani Zizadi, who is co-authoring this presentation, and Aykut Kars and Philip Haus. Here they are working on the project. These two people here, Richard Hegner and Carla Gimkiewicz, that now moved to industry that very much drove this kind of process development. And of course, I think all the partners being involved, and especially the funding agencies, including the European Union. So what is the future of electrobiorefineries? And today I will talk to you about the electrochemical provision of feedstock. So meaning we use electric energy to provide the feedstock for microorganisms. And the slide's a little bit crooked by there, but sorry for this. This seems to be a technical conversion factor, but I think I can still convey the messages. So, and the first time the concept actually was shown was in 2012 by the group of James Liao. So what they proposed in a very brief, one has to say, science article was to use electric energy to convert CO2 into formic, and then this formic is used by an engineered microbe for making C4 and C2 compounds. So, and this was proposed for the very first time, very prominently. But let's say the details on how this was done and let's say how well this is working and so on, they were of course not there at this time, and they were missing. So we took up this path in the lab, and finally we developed first a very seemingly simple, but at the end highly important and not so and delicate system that is robust at the end, but during development its handling was delicate, of course, to actually engineer the CO2 reduction reaction, so the totally abiotic electrochemistry is what I'm talking about now, into conditions where microbes could potentially live and strive. And at the end, we also showed they can live in these conditions. And we did all this, let's say, basic engineering in the 50 milliliter scale. You can see the setup here. And then the first thing that we did is, from this reference, but of course also from other literature, we generated something that one could refer to as a standard operation procedure. You can see all the details here, all the technical details. So we worked in 3 electrode setup with the 2 chambers, with indium as an electrocatalyst, and into pH neutral solution at 30 degrees and with 1 atmosphere of gas pressure of CO2. And you can see here how the catalyst was electrodeposited on the electrode and finally stripped off after usage. And I emphasize this so much because when you look in the literature and all the studies that dealing with this kind of reactions as well as others, you hardly find, let's say, an enormous number of replicates. It's more or less, it's very often very few ones. So this is why we worked on this for quite some time. And this you can see here, every single dot, it's not art here like a bird. It is a fully independent electrochemical experiment that was run by one of the 2 persons I have mentioned before, so Carla Gimkiewicz and Richard Hegner. And finally, they established a kind of standard operation protocol. So you can see here the Coulombic efficiency, which is more or less 60%. So this is a box plot with the same data of here. And here you have the rate of formation of formic within 1 hour. So, and this was the foundation that we needed and that we finally established to go on in our development, as I will show you on the next slides. So, but first thing was really to assure reproducibility. So, and what we then did was we changed systematically several parameters. And I will only walk you through one of these parameters. This is the electrode potential, because it has the highest impact, but also others like gas pressure, like conductivity, and so on, were studied. So you can see here, this is the electrode potential that we applied. Here in blue, you see the Coulombic efficiency, and here you see the respective rate of formation, here the current. And so you can see intuitively, of course, when we make the potential more negative, meaning we increase the driving force, the current increase. And by doing so, this is also quite expected. Also, the rate of formation of formic increases with more negative potential because we put more driving force. What was not expected at this time and can not fully be explained so far is that also the Coulombic efficiency, and this was already introduced by Ludo, or Faradaic efficiency, meaning increased significantly, close to 90%, meaning up to 90% of the electrons that we feed into the system ended up in our final product. I can go with you into detailed discussion about thermodynamics and kinetics of this if you want. We have some speculation, but I want to emphasize that this was not proven yet. So now we have something that already shows us we can make formic at a good rate. So, but the question also is how to put finally the biology and the electrochemistry together. And here we have different approaches. And the first approach you can see here, and this is closely related what Ludo already showed. But again, we have an abiotic electrochemical reaction here, though we have into one vessel. We reduce CO2 to formate, and then the microbes in the same vessel, they just use the formic and make our product. And then maybe we have a product separation and everything is good. So the second approach would be that we have a separate electrochemical cell and a biological fermenter while the microbes make our product, but still they are hydraulically connected, meaning the liquid is pumped from here into the biological reactor, recycled, and then again go into the electrochemical cell. So this has the advantage that you can scale the biological process and the electrochemical process independent in their size more easily than you could do in this kind of approach. But of course, it comes with the drawback that you need more pumps and peripherals and more all these kind of things. And the third option is just that, that you use electrochemistry, you make formic, and then finally use the formic. You may even concentrate it, put it next site to a reactor or ship it somewhere else and then give it to your bioreactor. So this would be the third option, that you have a fully separated system. So I will now focus further on more on the first two approaches with a strong emphasis on this one. So again, let's go back to this graph. So what do these numbers mean? So let's now assume that we need 1 gram of formic per liter an hour to be fed to our microbes. This is, I think, is a decent number to start with. So, and then we have a classical bioreactor. So it has these dimensions that you can read here. This is from one company. There are others one, but they don't differ so much. So if I want now to achieve this kind of feed and apply an electrode potential of minus 1.6 volt, like the group of James Liao did, I would need an electrode that has not the 3D structure. I come to this later on. That has this dimension. And as you see, it hardly fits in the reactor itself. But, when I go to minus 3 volt, only 1.4 volt more negative, I only need an electrode of this small size that readily fits into this 1 liter bioreactor to provide the needed feed of 1 gram per liter an hour. So there is a potential to really merge these two realms of electrochemistry and microbiology. And this, of course, is a good incentive to move on. And of course, this should not only be done at the 50 milliliter scale, so it has to be brought also to a process relevant scale. And here we come to a challenge that was also addressed, and this is the reactor development. And one thing that, let's say, people in biotech are very aware of are so-called continuous stir tank reactors. So they are standard in industry as well as academia. So people want to work in their standard bioreactors. But the problem is, in these bioreactors, you can see here, no electrochemistry fits in. So the question is, how can I bring the peripherals and all the features, better to say, that an electrochemical cell has into a bioreactor? And here, also in parallel to this development I've shown you, we also developed something that we now call an upgrade kit for bioreactors. And this allows us turning conventional bioreactors by changing the lid and some other details into an electrobioreactor. We can also model the hydrodynamics and so on. And at the moment, we are trying to, together with some companies at the end, to commercialize it, even that also you can use this kind of things in your labs at one day. So, but the short message is here, we can do electrochemistry in a process environment that is close to people that do biotechnology. And this, I think, is good because you don't want to scare them by having to do electrochemistry. So, and of course, then we also made some process engineering with it and compared these. So I don't walk you through all these numbers here of the 50 milliliter electrochemical cell and the 1 liter electrobioreactor. But also here, the key message is that at the end, of course, the 50 milliliter cell is still a little bit better, but the key performance parameter are not so far away from the 1 liter scale. But this is still only abiotic electrochemistry. Because what we want to do, and at this time we did it with some colleagues from Germany, Dirk Holtmann and his PhD student, Cora Kroner, and we also wanted to do some microbiology therein. And here we used Methylobacterium extorquens as an example, and this, because this microbe is able to use formate via the serine cycle and other metabolic pathways to turn this into mesacondyl R, which is believed to be a brick for polymers, for plastics or for polymers in general. And this is, just keep this in mind as one example. So, and what you see here now is again the use of this electrobioreactors in a two-phase system for didactic reasons, meaning we first did electrochemistry in the phase 1. You see here, formic is formed, then the microbes is put into the reactor. The microbes eat or consume all the formic, and our products, mesaconate and methylsuccinate, are formed. Again, as you can see here, the technical details, but of course we have to be honest. And honest in engineering means we have to crunch down the numbers. And here we have to say the total electron recovery that you can read here on the final line is only 1.5%. This means only 1.5% of the electrons that at this time, you see it's already some years ago, that we fed into our system via electrochemistry finally ended up in the product. And of course, this is not what we wanted. But of course, it shows first that the products can be formed, and this, at least at this time, was the first of this kind of balances at all. And there's a lot of room for engineering. So actually, it's very good news that we have there. And here is where Vivaldi comes into play. So because this actually what is the foundation, little bit the foundation of part of Vivaldi that I've shown you so far. And now I will want to talk about a few minutes what we want to do in Vivaldi to improve this electrochemical side. So we want, of course, improve the CO2 reduction reaction in terms of rates, efficiency, energy efficiency, and we also want to improve the product portfolio. And therefore, one way to do this is the implementation of gas diffusion electrodes. So porous electrodes were already mentioned by the speaker before. And what are gas diffusion electrodes is that we have a gas phase, and here we have the electrode, and here the liquid phase of the respective electrode chamber. So we are not limited by the solubility of CO2 in the liquid phase. We can directly feed it to the electrode. And then depending on the material that you have, you can get different reduction products. And of course, with the Vivaldi, we mainly focus on formic, but also methanol, because they are the most valuable feedstocks. And of course, this also brings challenges in process engineering. And so we working on the electrochemical cell design and also let's say how to use and how to improve the process solution. This is done with all the partners, of course, and I don't mention one name now because I will certainly forget otherwise one very important partner here. So you can see the whole outline of Vivaldi again here, and this, what I mainly focused on now, is the purification and conversion done by electrochemistry, but of course this is closely linked to all other working packages as well. You can also see what kind of products we are aiming within our EU-funded project here. And the take-home message is that we are working on the future electrobiorefineries on the more general level. So we are looking for feedstocks, here in this case it's CO2, and we want to improve, of course, all the processes by combining electrochemistry with microbiology. And thank you for your attention, and I'm happy to take your questions later on.
So, thank you, Falk. So we go to the last speaker of today, Ramon Ganigué, and we'll talk about pure cultures of Clostridium, and the floor is yours.
All right, thank you very much. Good afternoon. Thanks, Albert, for the invite. I try to honor the invitation with an appropriate title to Vivaldi. And I hope that you enjoy some of the work that we've been doing over the past 4 years. So my name is Ramon Ganigué. I'm a professor at Ghent University, the Center for Microbial Ecology and Technology. And I'm also affiliated to the Center for Advanced Process Technology for Urban Resource Recovery, capture in short. And I lead a group where we develop novel bioprocesses for resource recovery. Very big words, everyone works on these things. And I think what we try to do that is a bit different is that we try to work at the interface of physiology, ecology, and reactor engineering. So we are not scared to work at different scales, different disciplines, and try to get all the knowledge that we need, try to understand our processes before we do the engineering. And we work on many themes, and one of the themes that we work quite happily is CO2. I guess a day like this, 30-something degrees in Brussels, makes you think about global warming, but it's also a local issue, CO2. If you look at Flanders, where we are based, it's one of the world records in terms of CO2 emissions per square kilometer. So we are emitting 5 times more CO2 than the average European every year. So that's an interesting incentive to work. Also scientifically is quite interesting. So I hope that I'll have your attention for the coming 17 minutes. And the idea is that I'll try to give you a little bit of scientific background. It touches a little bit on some of the things that the other speakers have already talked about. The idea is that we try to use microorganisms to convert CO2 and other C1 molecules into let's say chemicals that can be of use. And in this case, we are using acetogens for that. What are acetogens? Some of you may know. For those who are not familiar with these microorganisms, they are strict anaerobes, and they come from very far in the ancient times, and they have a very interesting reductive pathway, the Wood-Jungle pathway, that allows to convert 2 moles of CO2 into 1 mole of acetyl-CoA that then can be converted into different products. And they are called acetogens because mostly they produce acetate or acetic acid, so they do C1 to C2 conversions. So as Ludovic has already mentioned, they are cheap biocatalysts. They replenish themselves. They are relatively tolerant to impurities. They can work at ambient pressures and temperatures. So it's all very nice. And it's also quite exciting when you start looking at what these microorganisms can do. So here you have an overview of the metabolic pathway that they use. They have 2 branches where basically they take CO2 and electrons, and you combine this carbon into acetyl-CoA, and from then you go to acetate or to other products. This is a metabolic pathway that happens at the thermodynamic limit of life. So this means they are very efficient at what they do, but also they cannot take a lot of stress because there's not a lot of energy that they can harvest from what they do. They have some advantages, but also some challenges. Let's not call them disadvantages. They try to produce acetate as their, let's say, final product. This means that they are very good at producing acetate. But if you want to go into other things, you need to either start doing genetic engineering or playing tricks, really understanding the metabolism. And a very important engineering challenge is the mass transfer. When we are using CO2, hydrogen, carbon monoxide as substrate, we are dealing with gaseous substrates. They are gases that are not very soluble, and to have decent rates, we need to really engineer these processes. But one interesting feature of this metabolic pathway is the fact that there are a couple of intermediates, and some that have already been mentioned here, that they are soluble and that they can be produced electrochemically directly from CO2, for example, formate, methanol, mentioned by Falk, but also formaldehyde. So if you can start feeding some of these compounds into the system, you might circumvent some of these issues that you are facing. So now that I've set the scene, I would like to talk to you about some of the work that this couple of students did in my team, looking at the production of isomers, how we can use different types of substrates to have process flexibility, and also how we can achieve high conversion rates. And following the theme of my presentation, I've divided it in 4 seasons, and we'll start with the spring. It's a warm season in Belgium, and I look at spring as a moment of discovery. There's new things happening, there's growth, and a few years ago we had an interesting observation. We had a reactor that was fed with methanol, and it was producing butyric acid. You see it here in red, and sometime around the day 100 we started seeing in green some isobutyric acid appearing. That was quite an odd observation because isomers are not something that microorganisms usually produce. We did some sequencing. You can see in red whoever was dominant, mostly during the butyric acid production, and in green we see this Clostridium sensostricto 12 popping up. So we did a little bit of quite a lot of work on isolation. We came up with some isolates, and to our surprise, it was an organism that had already been described a couple of years before, Clostridium luticellari, but the authors had not reported that it could produce isomers or that it could do the Bujungal pathway. So we got the strain from a culture collection just to avoid any biases by working with type strains that everyone can use, and then we started digging. So some of the things that we saw, we started by looking at the methanol metabolism. You see here on the left-hand side experiments with methanol, M, and acetic acid, so different electron concentrations of electron acceptor. Acetate 0 means there's no acetate, only CO2. And then we start adding a bit of acetic acid, 25 millimolars, 50 millimolars, 100 millimolars. And then on the right-hand side, we have a fixed concentration of methanol, acetic acid, and then adding also a bit of butyric acid, 25, 50, and 100. And basically what we saw is that when we add methanol and CO2, we produce a little bit of isomers, but as we start adding more electron acceptors, we see that there's more and more isobutyric acid being produced, to the point that here we have like around 70 to 80% selectivity. That was quite interesting. We started digging a little bit deeper in the physiology of this microorganism. We saw, we knew that it liked to grow at a pH of around 6.5. It's where we get like the highest concentrations of isobutyric acid here, like, I don't know, some 5 grams per liter. And then the concentration goes down as you get further away from the optimum. But what was interesting is actually that the selectivity increased quite sharply when we were moving away from the optimum and going into the extremes. So it looked like the extreme conditions really triggered this isomerization. Other things that we looked into in this first phase was the impact of CO2, because CO2 is also a substrate that is needed by the microorganisms, not just methanol. And we looked at the impact of CO2 availability, in this case by fixing the concentration of methanol and trying different concentrations of bicarbonate. So here, 10 millimolars, 20 millimolars, 30 millimolars. There's a lot of information on the graphs, but I'll try to guide you through it. So you can see like that every graph has 2 phases. We see in blue our methanol going down during the first phase in all cases, and in red our bicarbonate or CO2 being consumed. And then when all the inorganic carbon has been consumed, we go into the second phase. And what we see is actually that when we don't have inorganic carbon anymore, our methanol is not fully consumed, but it's when we have all the isobutyric acid or all the isomers being produced. So this means that there's some form of mechanism linked to CO2 availability that triggers that. You can see like a summary of the results here, more conversion when we don't have inorganic carbon limitation, but the isomers being produced when inorganic carbon is limited. So what we did quite a lot of work in bioreactors. I'm just picking one of them, where you see that we reproduced the batch first phase here. We depleted all the inorganic carbon, and then we started feeding methanol and CO2 in a fed batch. You see that during the second phase, we have linear production of butyric acid and linear consumption of inorganic carbon and methanol, circumventing that limitation. Good. That was a first story, but time passes and we are going to summer. And maybe some of you are looking forward to summer as a period of holidays, relax, resting. But I also look at summer as a period when you enjoy yourself. You do the things that you like to do. And some of the things that we like to do in our lab are really cracking the microbial black box, really understanding how microorganisms work, and really something that backed us was, why is this isomerization really happening? You'll see it later, but microorganisms don't gain energy or consume or dispose electrons out of this reaction. It's like 0 delta G. So why going through all the pain of having an enzyme to do this reaction? So we had like a putative metabolic pathway for that. And here we did some fundamental work with like carbon labeled substrates, butyric acid and methanol labeled at specific positions, some enzymatic assays, and also proteomics. I don't have the results of the proteomics, but I'll talk to you about some of the things that we did here. What we focused quite a lot was on this ICM enzyme, isobutyryl CoA mutase, which does the conversion between isobutyrate and isobutyryl CoA and butyryl CoA. Quite a lot of information. Also, I'll try to walk you through it. These are NMR spectra. You see here time 0, some intermediate time, and some end time point of our experiments, where we added a labeled butyric acid labeled at a very specific position, and then we looked at different compounds where the label was appearing, and we coupled that with HPLC just for macroscopic measurements. So on the left hand side you have the microscopic measurements, on the right hand side you have the NMR for the labeled compounds. Left hand side, macroscopic, basically you see your methanol gets consumed, your isobutyric acid gets produced, you consume a little bit of acetic acid. I'm not focusing on the caproic. And very important, our butyric acid remains more or less at the same level. But when you start looking at the labels, you may not see it here in yellow, but actually the labeled butyric acid that we added was almost fully consumed. So the net consumption that is not shown here is actually happening on this externally supplied compound. And we see that the label appears in the isobutyric acid here. Also quite interesting, and I'll touch upon that a bit later, we see that the label started appearing also on the butyric and, on the acetic acid and the butyric acid when we didn't add labeled acetic or butyric acid in a different position, which meant that the microorganisms, even if thermodynamically they can, it sounds like they could not be doing this, they are actually oxidizing the butyric acid or part of the butyric acid we are giving them and then using it back in their cycle. So that was also an interesting observation. I'll get into that a bit later. Similar type of stuff, in this case using NMR and 13 labeled methanol, just to confirm that it was following the classic with Jungle pathway. No surprises here. You see like a very good match in the products between, let's say, the macroscopic HPLC measurements and the NMR. For the sake of time, I will not dwell too much on that. And finally, some interesting things that we did with crude cell extracts. So we did some enzymatic assays for this ICM enzyme. We try to assess how butyryl-CoA was converted into isobutyryl-CoA and vice versa. And we established the rates of these enzymatic conversions. And it's the same enzyme going in both directions. And what we saw is that actually the rate of conversion of one direction is twice as high as the other. Why? I don't have an explanation yet, something we are still digging into, but it's much faster per unit of cell protein to convert butyryl-CoA into isobutyryl-CoA, so going into isomer direction than the other way around. Third season, spring. Some people like it, some people don't like it because we are getting close to winter. You can look at it as a season where we start shutting down. There start to be some challenges, transitions. And what we wanted to see of this microorganism is how it was doing when there was no abundant supply of methanol, which is a very reduced and nice substrate, but when it was challenged by other electron donors, like for example, hydrogen, or whether it could start scavenging wherever was available. So we repeated some of the work that we did with methanol, but with hydrogen, different color palette, different students have different preferences, so apologies for having to teach you that again. Very important, we see here cumulative hydrogen consumption in gray, acetic in green, and butyric in purple, and salmon isobutyric acid. And we see more or less the same conversion pattern. We have lower concentrations of butyric and isobutyric, but we can do exactly the same thing autotrophically, which is was to be expected, but it's interesting to see because sometimes the availability of more reduced or less reduced electron donors can change the product profile. We repeated the same experiments adding butyric acid, and we see that the butyric gets consumed and the isobutyric gets produced. But here we started to experiment a little bit more and looking at what would happen if we were supplying isobutyric acid externally. Are we going to get like double isomerizations? Are we going to get like longer compounds? But to our surprise, what happened is that we gave them the isobutyric acid and it just produced butyric acid. So it went the other way around. I mean, in hindsight, it's something that maybe we could have expected, but it's something that we find very strange because as you can see, going from one molecule to the other gives no biological incentive, no advantage to the microorganism. So I think at this point in time, we have good answers to what are the triggers for this isomerization, how is it doing it, but we have no clue why is it doing it. If you know it, you can approach me and tell me, or we can discuss. Other things that we started experimenting with was co-feeding methanol and hydrogen. So you see here on the left-hand side, the classic methanol growth. We give methanol and a bit of acetate, and we produce butyrate and isobutyrate, or butyric and isobutyric. So we wanted to see what would happen if we were giving also a bit of hydrogen. And we were expecting that to have like a deoxy growth. First, we would have like the isomers being produced, and maybe then we would start seeing like that, I don't know, something gets reduced or that the conversion goes a different way. But to our surprise, something completely different happened here. You see the methanol actually almost doesn't get consumed, and we see that it's mostly the hydrogen that is being consumed. So they are both co-consumed, something quite surprising because methanol is a way more interesting substrate. But when we started digging into this story, we found even more interesting things, at least in our opinion. You see here, this is the amount of CO2 that we have in the headspace. This is the methanol experiment. CO2 is never limiting. But what happened when we started adding hydrogen is that our CO2 got completely depleted. They didn't have any CO2 to grow, so they could not utilize the methanol. Why does this happen? Well, this is the classic with Jungle pathway. When you come here to methanol, most of the methanol goes into the reductive direction. But what happens is a small part gets oxidized and goes up here in the reverse direction. And you release CO2 and hydrogen. The moment that you have hydrogen in the headspace, this reaction becomes thermodynamically unfavorable. So you are basically blocking the conversion of formate to CO2. So the only thing they can do is to go down this direction. So you come up with a completely different stoichiometry. You start having more net consumption of CO2 apart from the hydrogen. And this you can clearly see here when you compare the stoichiometries for methylotrophy, autotrophy, and the mixotrophy, where you have different consumptions of methanol, hydrogen, and CO2, and different ATP yields. So this shows that these microorganisms are quite flexible in their metabolism. They can use different sources of inorganic carbon and electron donors at the same time. They can adapt to whatever is available. And you can play with that, for example, if you are in a scenario where you have like intermittent supply of green electricity, where sometimes maybe you'll have a lot of energy to produce hydrogen, maybe some parts of the day you will not have that. Just a last oddity, and we'll move to winter, which I'm pretty sure like everyone in the room is looking forward. Not because the presentation is boring, but because it's very warm for those who are at home. So basically, one of the other things we try to do is we try to add valeric acid into the fold. So changing butyric by valeric acid to see if we could produce isovaleric acid. And what we saw is not that we were isomerizing valeric acid, but actually that we were oxidizing this valeric acid into propionic acid. So the same behavior that we saw when we added the labeled butyric acid, we saw it here. And this is a reaction that is, in theory, not thermodynamically very favorable. We did some calculations. So if you were shuttling the electrons into hydrogen, this is never thermodynamically feasible. It's always endergonic. If you use them internally in the Wood-Jungle pathway, there is a narrow pH range when this is possible. And if you compare here experimentally the results at pH 6.5 and 5.5, you can see that here in pink we have the valeric acid being consumed, and here it can almost not be utilized. Good. And now we get the refreshing airs of winter, some snow. It's a harsh season, but also you can focus, you can get lots of things done. And one of the last things that I want to talk to you about is how we are trying to take all this knowledge that we got and bring it to the next level. We've done a lot of, let's say, pure culture work in small bottles, but we want to turn this into a bioprocess. So what we've done is we've assembled this hollow fiber membrane bioreactor where we can inject CO2, hydrogen in whatever proportions we want. We have here a buffer reactor where we can add whatever it is needed, and we are operating this reactor in continuous. You have like here a picture of the setup. It's a pure culture. It's a very much work in progress. So a couple of weeks ago, we had been only running it for 25 days. We had like first here a batch phase to let biomass grow. Here in blue, in orange, we have the acetic acid ramping up. And then we switch into continuous operation. It was very nice to see that actually our acetic acid concentration never dropped. So it's been increasingly going up. We also saw like the butyric acid starting to appear. And although we are at modest rates, 1 gram per liter per day, the objective is to increase that at least tenfold. Thank you very much. My take-home messages are quite in line with what I've been telling you. Clostridium luticellare can selectively produce and consume isomers. It can grow on methanol, hydrogen, CO2, also mixotrophically, which makes it an interesting organism when you have like intermittent availability of reducing power. And I think we have some promising results of the scale-up operation. So with that, I'll thank my co-authors, the funding bodies, and everyone who's at home or here. Thanks.
So good, thank you. So now it's time for discussion. So I would like the speakers to come in front, take a microphone. So we have some questions online as well as here, and I have my own questions. So maybe I will start breaking the ice and I will leave the turn for you. Take some water. Why do you want some water? Okay, so I will start with a question, and I think that that's a very general question, and maybe you can help me in seeing that. We all agree that we want to transform CO2, and here we have seen two potential ways that are always like in a rivalry, which is a chemical CO2 transformation or electrochemical CO2 transformation, and a biological CO2 transformation with their own pros and cons. So we're talking about yields, we're talking about rates, we are talking about possibility of scaling this up. So do you think that the future is one-sided? So if one scientific discovers a way, we're going to one-sided, it's a hybrid process. So, or it's, how do you feel taking into account the pros and cons with a direct biological CO2 transformation, or first an electrochemical, let's say, CO2 reduction?
Is that working?
No.
Yeah. According to me, I think we are not at a stage where we can decide for sure which way to go. So I think we need to investigate all the different technologies so that we can make a more educated decision later on, if that makes sense.
Yeah.
Do you want to? I could go on, but
Yes,
it's just
yes.
to start of the discussion.
Yeah, I think I can just support this as well. And also, I don't think there will be a one-fits-all solution. It's more that at the end, it's depending on the product, the specific volumes of the product, especially. So if we go for, let's say, high tonnages, or large volumes of the given product, then maybe get things like that with low price, and then maybe things like gas fermentation are more likely to be economically viable than. But when we come to more specialized product, then maybe also microbial electrosynthesis with pure cultures is something to consider. So I think there are a lot of, let's say, as I said, there's not a one-fits-all solution from my perspective. So we will see for all, let's say, products and processes, what the portfolio finally finds as best solution.
Yeah, I guess I also need to say something smart. I think because at Capture, like for example, we have the CO2 pipeline when we sit with like lots of people who are just purely looking at catalytic ways to convert CO2 to activate it. And they seem to be doing very well to produce certain types of molecules, but I think that's going to be quite limited. So I think in the future, in whatever architecture that you consider, you will need to interface electrocatalysis with biology if you want to do something with CO2. Whether it's in one pot, in two pots, I think we can say that at this point is difficult. We can probably also have our points of view, and we can agree to disagree.
I don't know if someone from the audience wants to add something on this or wants to ask a question. It's now the time, so I can continue with my questions. I have a lot of them, but so the next question that's also come up here, and also someone mentioned it in online, is also a classical question that everyone will have asked you. It's this controversy, let's say, on mixed cultures, pure cultures, the difficulties of working with pure cultures. I know that there is a lot of industrial processes that work with pure culture, so biotechnology is there for that. But in your presentations, you start with mixed culture. We found this, and then we decided. So I don't know what's your approach on that. Can you give?
Should I get started again? Yeah, of course I have an opinion. I've been working with mixed culture for 10 plus years. I do think there is a future for mixed culture, and especially in those type of environments, electrochemical settings where it's very peculiar environment. So it's quite easy to steer this mixed culture towards something you want and gain control over it. So I think we can. And historically, at least for microbial electrosynthesis, mixed culture systems have produced much higher like productivity, current density than pure culture driven MES. So from that perspective, there is an advantage for mixed culture. We still need to understand how and why that is the case. And the challenge, I think, is to gain control over the technology. And I think we have examples of mixed culture biotechnologies out there. So first in wastewater treatment, but also now in chain elongation, Chaincraft is also working with mixed culture to produce C2, C4, C6. So there are more and more examples of mixed culture biotechnologies out there. But still, I do believe there is a big advantage also to working with pure culture. We can gain control much more. We can know what it's doing at any given time. But I think there is some challenges to pure culture. Of course, the classic cost to keep it sterile, to keep it stable. Robustness is also less than mixed culture, and so on and so forth. So I think both avenues should be investigated.
Can I add something? So you say that a culture that it's enriched in a certain population can perform better than the pure culture of this population?
Well, I haven't done it myself, but there are people that have started with mixed culture and then try to build a synthetic co-culture. I think that's what you mean. And I've never reached the same performance because there is some intricacy to the mixed culture working principle that things are missing, that we miss when we do a synthetic co-culture. Pure culture are easier to operate than synthetic co-culture, I guess. But I mean, it sounds negative, but I still think we should investigate pure culture and synthetic co-culture as well.
I think slightly disagree. So I think we have to also, because I think that when it comes to other products than long chain acids, carbonous acids, then I think pure cultures, but also maybe synthetic co-cultures will likely outperform mixed cultures, because we also showed, I don't know who of you showed the thermodynamic limits at the end. So and it will never, let's say, be possible that to avoid that one of the microbes in a mixed culture that is not designed for this will eat. It's not eating up the product, and this is something that is very likely to happen in a let's say non-sterile, undefined mixed culture. So everything that goes beyond, let's say, caproic acid in its value and chain length and complexity, then I think it's more likely that we have pure cultures. And here also, there are some recent work from the Rosenbaum lab, for instance, that showed that the titers and the yields are not there as for the mixed cultures, but they are very close.
If I can comment, because I saw like someone made the sign.
Dieter, do you want to?
Make a comment. It's on that, but after you.
Okay. I also would like to disagree. Likewise, Falk, because I think there are historical reasons why people work with mixed cultures and not with pure cultures that I have to do, like for example with their background, their facilities. It's very difficult to work with anaerobic pure cultures in certain types of setups, and people just take shortcuts and use mixed microbial cultures without really considering whether that is the best approach for that. And if you think, like for example, for microbial electrosynthesis, if you take a group of microorganisms that can, and that's something that we've not even touched, whether the microorganisms are really taking up the hydrogen or the electrons, and I don't want to open that kind of worms, but the reality is that you might have many different organisms that can perform that function and that can actually take electrons in whatever form and carbon and turn them into acetate, and maybe doesn't have the genetic potential to produce anything else than acetate. And other organisms can produce butyrate as well. And then you start having microorganisms sitting in the same community that can perform similar functions and that will start producing, like if they can find their niche, start producing similar things, giving you like a mixed product profile. And this is just like on natural products, which are quite limited. We've seen it in the past, like we started doing this methanol fermentation work with mixed cultures, and we saw that it was impossible to have like a very clean, selective profile of isobutyric acid. We had to play all sorts of tricks to try to outcompete the other guys. And when we just went for isolation and we took the guys and we figured out how things work, we could identify what were the conditions that allow us to have like 80-90% selectivity without having to go into, I don't know, like playing with very extreme pH or doing some tricks. So I think mixed cultures have a spot for certain applications. I just don't know, like beyond the C2, C4, C6, if we will be able to do anything more with mixed cultures. And I've seen many people, respected scientists, trying to do other things than this with mixed cultures and not being very successful. But please.
Dieter.
Yeah, I wanted to extend. Maybe yes.
Yeah.
Okay. I'm trying to extend from there. So if I understood correctly, you speak of mixed cultures mainly as let's say a mix of strains that are there side by side, and one might take over and do the majority of the job. What about thinking of mixed cultures as, let's say, a collaborative community where, for instance, part of metabolism is done by one strain, handing over, now very picturesque, an intermediate to another strain that is further converting that. And that's, of course, more something, finally, a concept for a sterile community. But could you extend on that?
It's quite important to make a distinction here between what we could understand as an open community or undefined community in a synthetic community, which is something that Falk has already mentioned. And when we have an undefined community, we select for a function of microorganisms doing something. We don't actively handpick who's going to be there. And it could be that we have organisms there that we don't desire to have, and maybe they will have, have a negative function, parasiting some of the products or competing for substrates. There's quite a lot of interesting work into assembling synthetic communities where like there's division of labor, and they try to do that to get to certain products. And that's very much an interesting avenue that people are exploring. I just like want to fall back to what I was saying. I think my comment was going more like into the undefined mixed culture where you have and it has evolved from the environmental biotechnology mindset where you don't know exactly who is doing there, but you give them the conditions to do a certain function, to perform a certain something. But like in the past, we used to use this, or like we are still using this, let's say for destructive reasons, for, like degrading something. And when you go for something that is very complex to something that is very simple. And like, for example, anaerobic digestion does this very beautifully. But if you try to do the opposite and go for something that is very simple and many organisms can use, and then try to produce something that is very complex, chances are that you'll have many people, nibbling there, and you will not get to, especially like in biological CCU, where you are looking at a process that economically is already very challenging. Like it's.
Yeah, I'm mainly thinking of specialized synthetic communities.
Maybe.
Yeah, this is what I meant, but maybe wasn't clear enough on this. So, but Ramon nicely, just explained the advantages that we have there with this kind of cultures.
Thank you.
I do agree, by the way. What I meant by gaining control is also product diversification. I agree, mixed culture, we have an issue there. But we should also think about process conditions, right? Depending on where you get your CO2, where you get to your water, you also have advantage to using mixed culture if you target products that can be naturally produced, because then you might not need to clean it that much, depending on where your CO2 comes from or where your water comes from. So then you also have to think about that technologically, economically, environmentally, what you want to do, and the product volume and all these things needs to be considered when you decide pure culture, synthetic co-culture, mixed culture. So yeah.
Okay. Another one of mine. So this workshop is about going from CO2 to long chain fatty acids, no? And I want to focus now on this concept of long. So what we've seen from Ludo and Ramon, we are C4, C6, and with the approach of first conversion to C1 that can serve as a feedstock for whatever you want. Maybe you can go longer than that. So what's the concept of long for you? Or how long do you want to go with this chain? Or you think that under your approach there should be let's say, I don't know how to put that, like a maximum length that you can build from a thermodynamic point of view, and then we will have another one to grow on that? Or
Why me all the time? I don't know if I have an answer to that one. I think it really very much depends what you want to do, right? I mean, you could also have a multi-step process. If, let's say, you produce only C6, which might not be long enough, but C6 can be a platform chemical to either convert it enzymatically or chemically afterwards to longer chain compounds. Whether you want it as a fuel or as a flavor or as plastic, you can do a next step conversion, right? So, but your question was about in one system, how long can we go? Go ahead.
I think there are two ways that we can look at it, and we have them both here. We are producing what we produce because that's what microorganisms can do naturally. So we have a limitation and a bottleneck, and what you are doing in Vivaldi is you're looking at molecules that are interesting industrially and trying to find ways to do that. So I think that we need to see what is technically or biologically possible with natural organisms, or like even engineered systems, engineered microorganisms, but also keep in mind what industry wants. We can produce like very long molecules, but like if there's no uptake for them, turning C2 into something that people don't want and that is more expensive than just emitting CO2, that doesn't make a lot of sense. So I think it's a challenging point because it's a chicken and egg situation where you could be producing certain compounds that don't have a market yet, but then it's very difficult to justify that you try to develop something on the promise that if you can do this, the market will grow exponentially, and like you'll be able to use that. I think there's a technical side to that, which is downstream processing. I don't know Vivaldi enough to see like how you are tackling that, but like it's usually the thing that like makes or breaks a bioprocess. It can be like, I don't know, 60% of the cost of a biotechnology, and you need to look for compounds that can be easily separated in whatever form. And like, for example, I'm thinking if you look at acetic acid, that is something that we can produce rather fast, rather nicely with like mixed or pure cultures, but it's something that has a very low value. It's very difficult to get out of the water, and that you will need to, I don't know, like find ways like produce oils or polyhydroxyalkanoates or microbial protein or whatever, if you want to do something with it. And if you look at other compounds with like a higher added value, I don't know, like succinic acid or so, maybe you have more margin to build your downstream processing to get them out, and maybe their properties are also more favorable to separate them.
Apparently, you know Vivaldi better than you think. So this is actually what we are doing on the project, and going back to the question of length, I think this is not what's important at this point for the approach that we in Vivaldi follow and that I've shown here. It's more the matter of complexity, and also complexity of a molecular sense, like stereoselectivity, like making only one isomer and not racemic mixtures, because this also creates value at the end. And this, I think, is what this, let's say, integrated electrochemical biological process has its strength at the end. And this is also something, as was already emphasized, that we are following here as well. So having the, let's say, ability of electrochemistry to use electric energy as well as CO2 to make something simple on the first glance, that then can be used by microorganisms to make higher value, more complex molecules in a selective way. So we finally, I think, we combine the best of both worlds.
Yeah, my question was that if you see your process as a first step, not a full, that's good. I have a specific question for Ramon and a specific question for Ludo. Ramon mentioned that the selectivity of the Clostridium strain was better out of their optimal conditions. Do you know which could be the reason?
No, we don't know why that stress increased the selectivity. I mean, it's still a very much work in progress, but yeah, I mean, I think industrially it doesn't make a lot of sense that you improve the selectivity by a lot, but then in exchange your titers, your concentrations drop.
Okay. Ludo, you said that is mine. Eh? So you said that you think that it's better to work under continuous mode than under batch, and you said something that because batch brings a lot of limitations to this process of MES, but you know that most of the people doing research on MES is working on batch mode and MEC. So can you just point out what are we doing so wrong working under batch mode?
My message was not that you are doing something wrong.
Yes, which are the drawbacks?
I can only speculate at that stage. We are looking into why. I mean, the most logical thing is that you run out, like there is a key nutrient that is running out in batch operation that is not running out in continuous. Mm-hmm. Which one it is, I'm not sure yet. Another thing is that maybe some of those metal-based nutrients also get electro-reduced in batch, and then you run out of it. But again, that's only speculation. We just do know, and we do see very big difference when we run batch for like 100 days and nothing happens, or just a little bit of production, and then you switch to continuous and it just goes crazy. But let me think, do I have other... the CO2 part, but that's a bit different as well. I mean, a lot of people also work in just like sparging one CO2s and letting it being consumed and then sparging again. I think that creates some limitation as well compared to continuously sparging.
But that's the same of working under continuous conditions and having a high conversion. Then you will work always under substrate limitation conditions. So in your case, you say continuous is better because you don't have
limitation,
a good conversion, or let's say a high conversion, and there is always substrate in the medium, no?
Yeah, so we are talking still lab scale, right? So we need to indeed see when we scale up, because especially when you look at CO2, right? You want to end up with a high conversion efficiency, so not having much left at the end of your process. And same thing for nutrients. You don't want to feed too much because it has a cost. So you want to avoid that. But we are not yet at a point where we do medium engineering, as I call it. So we really need to identify what compounds are limiting and how can we engineer a medium that allows no limitation yet being economic.
I guess it depends on what you want to convert and what, I don't know. Do you want to add something, Falco, Ramon? Batch versus continuous?
No, I think.
Okay, good.
If I may,
yes, please.
I think that an important consideration here, like in bioelectrochemical systems, is like the way that people achieve very high concentration. But let's say there's always a trade-off between rates and concentrations. And I think that you need both industrially. And it was quite nice to see that in your system you can have very high conversion rates and high titers. I mean, they are not industrially relevant. But yeah, like traditionally how people achieve high concentrations is by working in batch. And how people achieve high rates is by working in continuous at low concentrations. So I think like in the future, in whatever form you go, batch or continuous, we just need to be able to achieve both at the same time.
Yeah, and talking about concentration, you need to also be careful with product inhibition, because with this type of product, it becomes inhibiting quite quickly. So that's also a challenge, because you would like high concentration to decrease your cost of downstream processing and product recovery. But then you go high concentration and then you limit your microbial activity. So there is a trade-off between process consideration and microbial consideration to have.
I have another one. What? Okay. I have a lot of questions. I'm sorry. So another thing that I think it's very difficult in our case, and this is particularly for Falk and Ludo, is about the cathodes. So when I think a lot of people that starts this research, chemical engineering, okay, I can manage with that. Biotechnology, okay, I can manage with that. I have some friends that know biotechnology. But then you go to cathode materials, you go to the new advances that are being now, and I have the impression for the big amount of papers that I see related to cathodes that improve a bit hydrogen production in a MEC, or that, for example, can produce or can reduce CO2 to many different things. I think that now there is kind of a boom of people finding new materials, and I would like to know your impression about that. How is it advancing, and how do you think that if really the cathode material is going to be the very important thing to improve in both cases, like the hydrogen production, or maybe or in your case, I don't know. For me, I think how important do you see this, and also thinking in scaling up, because finding new cathodic materials that are very, very good, but they are too expensive that you can only buy like two square centimeters. I don't know.
So
Falk,
just a question back. So we're talking again about MES, like Ludo presented, because when you think about CO2 reduction reaction, which is also a cathode, like we follow in Vivaldi, I think the story is a little bit different, because here we speak about a abiotic cathode, whereas when we have, let's say, biotic, or in a pre-sense of microorganisms cathode, that's different. So you want to have both cases, or more focusing on the
because I think that in both cases there is a lot of research on the cathodic side. One for microbial addition to increase hydrogen production, and in your case, of course, to increase selectivity, yield rate.
Yeah, I can say, of course, the electrode development is quite important, but it's a complex matter. So I think we should talk about some, let's say, some specific things. So of course, at the end, the electrode material has to be, let's say, scalable, economically viable, and so on and so forth. And to make things scalable is something like also some people's work on, of course. For instance, by scaling gas diffusion electrode that I introduced in my talk. And here also things like fouling, because when I speak about abiotic electrochemical reaction, I don't want to have microbes in the vicinity, because then the microbes may block the pores and then hinder actually the wanted electrochemical reaction. So, and therefore things like engineering solutions like backflushing, like pulsing, to remove all these microorganisms that are detrimental in this case, is an option. But this is when we talk about, let's say, I want to have an abiotic electrochemical reaction, and the microbes they just hinder this. The story is a little bit different in the case what Ludo presented, that we want to have microorganisms actually that being close to the electrode, taking either up electrons, or I think, Ramon, now we have to talk about this, or the hydrogen that is formed by the electrode, or even other compounds, because there are also studies now indicating if you put an electrode and a negative potential, so a cathode, into a microbial broth, so with time you have an electrodeposition, so the elements are not only removed in the batch modus as nutrients from solution, it's also that they form let's say, electrocatalysts. At least we can have indications of this. Yeah, I'd say we have indications now from different groups that we have an in situ formation of electrocatalysts, and so maybe some of the work in the the early work on microbial electrosynthesis that we have seen, where people thought microbes take up either direct electrons or take up hydrogen, are also related to the formation, the in situ formation of an electrocatalyst by metal deposition, like indium, maybe like tin, like copper, very likely. And then on this metal particle, we have the reduction of CO2 to C1 compounds, like formate, maybe formaldehyde, methanol, less likely, I would say. And then the microbes eat it up. And this could be, but it's still speculation. But because in this early works, as you said, we have the issue that sometimes for months people don't see any activity, and then after a very, very long time, all of a sudden there was an acetate formation. So we don't know this. But getting back to your question, Albert, I think yes, electrode engineering together with reactor engineering is something that we have to consider in a scalable way. But I think there's not a one-fits-all solution. So there are, let's say, solutions where we have high rates on the electrodes, where we have also high Coulombic efficiencies on the electrodes, and then maybe the separation, the physical separation of the electrochemical cell from the microbial broth is the way to go, because then I can scale up the biological reactor, as big as a house, while having a small electrochemical cell next to it, which also decreases my capital expenditures. But when I have, let's say, lower electrochemical rates and let's say still and also low microbial productions, then maybe it's sufficient to hang in some electrodes into a big tank and have them doing the job. So again, there's no one fits all solution from my perspective. We have to see for every case what's the way to go.
All right, so that's a lot being said already. So I agree with most of it. And there's several things to answer. We've already, like, just a small parenthesis, like I remember even in my PhD, I demonstrated copper and iron particles deposition. We assumed that it was towards hydrogen at the time, given the potential we were applying, but it could indeed be towards formic acid, most likely, or others. So if I want to add something else than Falk just said, I think electrode material design is important, but as Falk said, it has to be together with process design. So I see in literature, a lot of the electrodes that are being tested or designed are in non-optimized system. And a lot of the conclusions that are drawn from these experiments might not be true towards the systems that actually can be scaled up. So there is a little bit of a caution, I would say. We should always test electrodes or organisms in an environment that makes sense towards application. But it is important, but I also show that, I just used in my slides, I just used commercial carbon felt. No pretreatment, pretreatment like acid-based treatments and plasma treatment to make it hydrophilic, but that's it. I didn't modify that electrode or whatever. And it's still possible to get high performance. So my strategy is to first design a reactor that makes sense and then start testing new electrode materials. And then it's going to be difficult because indeed, like if you saw the graphs that I make from that opinion paper, most work has been done on cathode development. And now if I want to test good cathode materials in my reactors, I have to go through a lot of literature to find out what could work in my system. So yeah, it was just to add another layer to what Falk said, but I agree otherwise. And there is, to be clear as well, there is a lot of work done in catalyst development for abiotic CO2 electrolysis as well. Like a lot. Like the field is like maybe 100 times bigger than microbial electrosynthesis, or 1,000 times bigger. And it's on a daily basis. You have papers coming up with new electrode material or new GDL, gas diffusion electrode, and things like this.
Just a short comment on the last sentence. Yes, there are piles of papers coming up every day, but most of them, as far as I see at least, they are not on a technical scale. So because it doesn't make sense for the things that we are doing to have a 10 micron to 10 micron high performance catalyst at the end, but we need something that is of practical relevance. And this is not as often shown as we would hope for.
Yes, agreed. So that was the last of my smart questions. Then I have some questions that I can ask them during the coffee. So maybe I'll give you the last opportunity to the audience to do a question, because then.
Hello. I got a small question for Ramon, or maybe a consideration. I might be speculating here, but you said that your strain of Clostridium that you identified was able to consume butyrate and isobutyrate, and that you don't see an advantage from a thermodynamically approach. But have you considered evolutionary and even competitive approach, like the mixed culture from which this strain was isolated? Isobutyrate, or even concentrations of the isobutyrate could be toxic for some of the strains that are found in that mixed culture?
Yes, so indeed toxicity is something that has been put forward as a potential hypothesis, but in some of our experiments we've seen the onset of the isomerization from time zero. So when there's almost no toxicity by other organic acids. So although we don't have a, let's say, 100% proof of that, I tend to disagree that that could be a strategy. I mean, of course, it's a very good remark, and this is something that I've already mentioned. No, we are trying to take microorganisms that have been designed to do certain things in nature, and we want them to do something else. And we need to start playing lots of tricks on them, making them work in conditions that they don't. I mean, what's the point of a microorganism that produces succinic acid or isobutyric acid in nature? Or, from methanol. Is there a lot of methanol in nature? So they occupy very small niches. Why was it doing it initially? Was there where does the isobutyric acid come from? You can have, I think it's the degradation of valine, one of the amino acid gives isobutyric acid. So it could be that this microorganism evolved to take advantage of that substrate, and now it can do it in another environment. But I think looking at the process, if your butyric acid and your acetic acid are not at toxic levels, why would you isomerize? And I mean, producing an extra enzyme is not a big metabolic burden, but is energy that the cell needs to invest. And I believe that microorganisms are very smart in regulating how they use their energy. They are very stingy, and they are only going to produce an enzyme if they really need it, or that if it gives them an advantage. So we've not been able to square the circle. We don't know why this is happening. It's a very interesting remark, like the evolutionary history of this microorganism and why in the first instant has this capacity. Maybe you will enlighten us.
Just a very small point. Could it be that it's a promiscuous reaction of an enzyme that does something else in nature, in the natural environment?
The truth is, we've tried to use this microorganism to do other types of isomerization, and it can only work with butyric acid and isobutyric acid. So it seems to be quite specific, that this organism has very high specificity for this type of conversion. And maybe we are not smart enough to make it do other things, and we are in a completely wrong track. So it's a very valid remark, and I'll take it home and we'll turn it around. Yeah, because it could be we've in a completely different project. We got an enzyme that we thought it was that the cell that the microorganism had it for hydrolytic reasons. And after trying hydrolytic tests, we've realized that it's crap at hydrolyzing those molecules. And by looking at possible functions, it could seem like it has a role in membrane fluidity. So it could indeed be that it has a different role. We were hoping that maybe like from proteomics or some omic analysis, we could get like better insights. We are still a bit bogged into the data analysis to see if it will actually provide some closure into this whole like enigma of why is it doing it. But thank you very much. Very, very interesting thoughts.
Thank you. So I think I will close the session here. First, a big hand to the speakers. Thanks. And also from Vivaldi, you have here, if you want to follow us on our social networks, and thanks for being here and on the net. So see you next time. Thank you.